welcome to lesson number 5. I think we're on number 5. We're starting chapter 12 in your textbook, page 199. This chapter is solutions and colloids. Solutions and colloids are all around us. The air that we breathe is a solution of mixed particles. Some of them are even solid particles, such as smoke. Smoke is actually a mixture of solid particles that are floating around in it. And water droplets of fog. The fog is actually physical water droplets, and they're all intermixed into the air. So there's lots of these colloids and solutions. Your body is made up of colloids and solutions. The cells of your body are bathed in an aqueous environment that has ions such as sodium and potassium and chlorine ions, and molecules of glucose and everything are all, and larger proteins, they're all intermixing and working together in the body. And in fact, the ability of something to pass between, if we have a cell wall, and we'll draw a circle here and say that this right here is the cellular wall, one of the main transporters of certain types of food and information and all that through the cell happens due to the make sure I use the difference in concentration. So if there's a higher concentration of stuff outside the cell than inside the cell, it will go through the cellular wall because of this colloidal solutions. And so if you take a sugar cube and you drop it into a glass full of water and you let it sit there and stir it in, and that it will totally dissolve into the water. And if you take a super high powered microscope and look at the water, you still won't see any sugar. It'll totally dissolve into the water. And so it will be a colloidal solution of sugar water at that point. And at this point, it's called a homogeneous mixture, which means that it's evenly distributed throughout the whole solution. It's not clumped over here. We talked about homogeneous and other types of mixtures, and the homogeneous one is when it's evenly distributed everywhere. So air has oxygen and carbon dioxide and nitrogen and a little bit of argon and all these different things floating around in it, and it's all evenly distributed. It's homogeneous. Okay. And this, in the case of the water and the sugar, it would be that same way. It would be a homogeneous. And so when you have a substance that dissolves another, the substance that does the dissolving, so with the water and the sugar, when you have a glass of water, it would be considered a solvent. So it would dissolve the sugar, and the sugar would be considered the solute that goes into the solvent. And so anything like that where you have a solid and a liquid, then it's pretty easy to tell which one is the solvent and which one's the solute. In a case where you have two liquids, it's a little bit harder, like which one's the solvent. And in that case, for the purposes of chemistry and of science, then we say that the one that has the larger volume is the solvent, and the one that has the lesser volume would be the solute. Now, on page the top of the page of 200, there's the solution types, and we'll kind of go through those really quick. So there's gas, solvent, and gas solute. So, like air. And in that situation, you could have oxygen, carbon dioxide, water vapor, traces of other gases. And as we mentioned, for deep divers, they'll actually swap out some of the nitrogen and replace it with helium. All of that would still be a solution of gases. Both the solvents and the solutes are all gases. Now, you can have a solution of liquid and a gas. Probably the most common thing that you would be familiar with would be like a carbonated beverage, like soda. There's actually gas in solution that's trapped in solution at that point. And then you can have a liquid and a liquid, such as vinegar, which is acetic acid and water. A lot of your different things like that are. You can also have something like automobile coolant, like your, what's it called? The coolant. Glycol and stuff that you put in your radiator to keep your engine from freezing. That's a mixture of water and the glycol and stuff. You can have liquid and solid, such as like the sugar, or seawater is a big one of this, or salt water like at the Great Salt Lake. If you take the water and then you take that salt water and let all the water evaporate off, you'll be left with the solids of the salts and stuff, but it's all intermixed in solution while it's in the ocean, and there's a lot of other minerals that are intermixed in there too besides just the salts. You can have a solid and a gas. You can have hydrogen and palladium and stuff. I don't know a good way or a good example of that one, but you can have a solid and you can have a solvent with a liquid solute. That would be, and I don't think this is used as much anymore, but the amalgam that they used to use for dental fillings that had mercury and silver that would be kind of together, and the mercury would be a liquid in the solid, and I don't know of a lot of other examples of that really right now either. And then you can have solid and a solid, which would be sterling silver, which would have some copper in the silver. So the silver would be the solvent, and copper would be a solute that would be in it. Stainless steel, you would have chromium in the iron. So we've talked about a lot of these, and they're all considered actually a solution, where a lot of times you think of solution as only a liquid, but for the purposes of chemistry and that, there's a lot of different solutions or mixes. So we're going to talk next a little bit about miscible and immiscible. Miscible is when a substance, in whatever phase it's in, that are completely soluble in the other one. So, like when you put salt into water, it will is completely soluble in water. That would be a miscible mixture. Alcohol in water, or gases, like you mix oxygen and carbon dioxide and everything, and they totally intermix. There's no fighting with their wanting to be mixed together. Immiscible example would be something like oil and water, gasoline and water. You try to mix them together and the oil will float on top of the water. It doesn't want to mix. You can take and stir oil into water and let it sit, and it'll all bubble to the top. Okay? It doesn't like to mix. That would be immiscible. And partially miscible would be something like bromine in water. There's a picture in your book on page 200 that shows a mixture of a partially miscible, where parts of it are in the water and parts of it aren't. So something that's fully miscible, well, no matter what your mixes are, they'll totally intermix. Where bromine, water can only absorb so much, and then the rest of it drops out. And something that's immiscible will completely separate. Hopefully that makes sense with what I just went over. Especially when you read through it, I think it'll make more sense than that. So the solution process, for instance, if I put sodium chloride in water, so we'll draw some sodium chloride that we're going to put in water. And we're going to put it into some water here. This is not really a chemical mixture in this same way, but when we put them together, then the ions disassociate with each other. And when an ion or a molecule is hydrated, it is said to be solvated, and the molecules are totally surrounded, or the ions in the case of salt are totally surrounded by the solvent. There's not like a clump of it and then water around that and a clump of it. They all completely become fully solvated. And factors that can affect how fast that happens, that can affect the rate of solution or its ability to become in solution, would be mixing. Like if you put sugar in the bottom of a bowl and then pour water in it and you look in there and goes, it didn't dissolve. But you take a spoon and start stirring it, you will speed up how fast it does the dissolving. Also, you can mix it with smaller particles. Like if you have chunks of sugar cubes and you sit there and mix, it's going to be a lot harder to get that to mix with water than if it was granulated or something like that. So granulated sugar, when you mix it, even if it's the same amount, would go into solution much faster. And then another last thing that would help it go into solution would be to add heat. And the reason why that would increase its rate of going into solution is that as we heat things, as we've talked about many, many times, that makes the molecules move faster. And as they move faster, they're going to bump into each other more. And that's going to help them to get spread around and to separate and to become completely in solution. So that's the end of lesson number 5. And we'll see you next time.